Okay, in 2.2 Atomic Theory Notes, we are going to discuss Rutherford to the Quantum Mechanical Model by Schrodinger. So here's the Thomson model. Rutherford, in his gold foil experiment, tries to answer the question, test if Thomson's atomic model was indeed true, that protons and electrons were randomly dispersed. He used recently discovered radioactive substance that produces positively charged alpha particles. These are two protons and two neutrons that are hugging together. So you can send a stream of these towards a thin slice of gold foil with thin layer of atoms and see what happens. So he predicted that the alpha particles will go right through a thin gold foil without any deflection, as shown in this model over here. Here's the thin gold foil with the dots showing electrons and the alpha particles going right through in blue. He used a thin screen to fix the gold foil, and he had a source of alpha particles inside a lead case with a thin window that allowed the particles to come through, and then he surrounded the gold foil with a circular screen to capture any alpha particles that were deflected or went right through. So it was coated with a fluorescent paint so that any charged particles landing on it will produce a shine as shown here. So here's an image of a particle going through. So here is his results. Most of the there was a big beam of alpha particles coming through that he couldn't see, but I have made you see it. And most of it went right through, showing a big flash right on the opposite side. And then a little bit was slightly deflected, and about 1 in 20,000 were hugely deflected. You need to draw this diagram and understand how things work. So here is what he saw. The major deflections were caused by 1 in 20,000 alpha particles hitting the center of a tiny, small, dense nucleus that was placed in the middle of the atom. The minor deflections were alpha particles hitting the side of a nucleus, causing a minor deflection. Alpha particles are positive, so that's why when they hit only a positive particle, they would be deflected. So Rutherford said this was the most craziest result he has ever seen. It was like shooting a tissue paper with a bullet, and somehow the tissue paper made the bullet come towards the shooter. So here are his conclusions. And I want to discuss the last one. Since most of the alpha particles went right through, that means most of the atom is made out of empty space. I discussed the other two earlier. You need to know all of these. So here's the Rutherford model. The tiny dense nucleus is now placed in the middle, and there are no positive charges around, and the randomly dispersed electrons are now nicely arranged around the nucleus. So some discoveries. 1914, Rutherford discovered positively charged particles that went in the opposite direction in the cathode ray tube. He called them protons. And in 1923, Robert Millikan experimentally determined the mass of an electron using the oil drop experiment. And in 1932, James Chadwick discovered a neutral subatomic particle that he called neutron. So now all three subatomic particles are discovered. By the way, an electron weighs 2,000 times less than a proton or a neutron. There was an issue with Rutherford's model. For example, when you heat a metal, the metal atoms absorb that heat energy and turns into a shiny, almost yellow color. And then as they cool down, releasing that energy, they turn into a red and then a gray color and go back to their normal color. Rutherford's model doesn't explain this. So if you think of a specific amount of energy, say 10 joules of heat energy, it is actually made out of little packets of energy, as shown here. So that is kind of like $10 of money instead of 10 joules of energy is made out of many, many pennies. Pennies are the smallest quanta of money. I hope you understand the idea of quanta. So, in 1901, Max Planck proposed that energy was quantized, as I have shown above, and that matter could absorb or emit energy only in multiples of small units of energy called quanta. Then in 1905, Einstein explained the photoelectric effect. This is a phenomenon that has been observed for a long time, but nobody had an explanation. Basically, when light shines on a shiny metal, electrons from the metal can be ejected based on the intensity of light. This is how you make solar power out of solar panels. Anyway, Einstein found that only specific energies of visible light can eject electrons from metal. And he said that light is made out of particles called photons. That led Niels Bohr to think that electrons that were ejected also had energy that were quantized. So he included an explanation for how energy of an atom changed as it absorbs or emits energy, light energy, based on Max Planck and Einstein's finding on quanta. So, electrons in Bohr's model, which was called the planetary model, he did no experiments, just based on other research that was published. Electrons are found only in specific circular paths known as orbits, shown here. So, electrons orbit the nucleus like planets orbit the sun. And each orbit has a fixed amount of energy called an energy level. So here are two energy levels. The quantum is the amount of energy needed to move one electron from one orbit to another, or energy level to another. And here's a quantum. It's the difference between the energy in the two energy levels or quanta. And he said electrons can jump from one orbit or energy level to another by gaining or releasing a quantum of energy. Now I'm going to show you a small animation. A star-shaped piece of energy is hitting an electron, and then the electron jumps one quantum above. When gaining energy, electrons move to the furthest orbit from the nucleus, because those orbits have high energy, and when you lose energy, you move back down to an orbit close to the nucleus. Then the quantum mechanical model of the atom. So, this was based on two ideas, one by Schrodinger suggesting, based on math equations, that electrons move like waves around the nucleus, not as particles. And at the same time, Werner Heisenberg has proposed the uncertainty principle, saying the location and velocity of an electron around the nucleus can't be measured exactly, because if you measure one, you change the other one. This led to the idea that electrons possibly move like waves and particles. So, Erwin Schrodinger put these two ideas together and proposed that the electrons are located electrons can be in so many places at the same time around the nucleus. So electrons move so fast. So he proposed the idea of electrons existing in a cloud. Later, it was they were added orbitals into the idea that electrons live in orbitals inside the electron cloud. When you take all the orbitals together, then you make the electron cloud. So what is an orbital? It's a three-dimensional region, not legion, of space with a high probability, 90% probability of finding an electron. So it's like a house. An orbital is like a house with a specific 3D shape in which you can find an electron at any given time with a 90% probability. So the quantum mechanical model is influenced by Heisenberg, Schrodinger, and Bohr. And so here's the quantum mechanical model. Contrast it with the Bohr model, the planetary model, where electrons move like particles, but here they move like waves and particles. And that's all I have for you today. So let's look at the summary of all the atomic models. Here's Dalton's model, the plum pudding, Rutherford's nuclear model, Bohr's planetary model, and finally the Schrodinger model, where the electrons move in a cloud and the atoms are not fully solid. The nucleus is solid, but the electron cloud is squishy, and that's it. I'll see you in the next video.